Okay, so today we'll continue on this. I started the recording. It's okay. Yeah. So today we'll continue on this partial wave methods, and basically I'll set up the problem which I did partially last time, and then I'll completely set up the problem. And as you have noticed last time also, that it's basically the main thing is to describe the problem. And after you describe the problem, the main thing to calculate will become this phase, the phase shift of the outgoing wave compared to the incoming wave, which is basically the S matrix. And we will show how to we'll give a general strategy of how to calculate it, and then we'll do one examples. And there are after that, as usual in this part, the formalism is so tight. Once you set up the problem, then the rest of the job becomes extremely trivial. And if you have gone through the pre-recorded lectures or notes, then you already know that that is the case. Now, that is basically the main plan. And then if there is some time left, I'll start doing the Green's function, which is another very elegant and very simple method, which is just extending the Green's function as you learned earlier, and in math methods or electrodynamics, just to use this kind of scattering problem. And that's a very powerful technique. That is actually the main technique which is used in most practical problems. And I will do the Green's function formalism probably over tomorrow also, and that will also be boiled down to calculating. Again, the formalism is so tight, it will eventually boil down to do some simple calculation, and then there will be a generalization of that in a bracket notation, which is Lippmann-Schwinger formalism, and unlikely that I will get time to do that. It's same thing, just done in bracket. So I'll suggest you to go through it in the pre-recorded and lecture note, because by Wednesday I want to get into the relativistic quantum mechanics, for which this year I'm getting only 3 lectures. So let's see how much I can do justice to that. Okay, so with this outline, so let's go over the simple points which I mentioned last time. That the main point of partial wave method is this Huygens principle. While you describe the problem with some incoming plane wave and some scatterer, and after scattering it becomes some spherical wave. If it is a point scatterer, if it is an extended scatterer, it can be some distorted spherical wave, and we'll find the distortion factor. But what is important, that we are dealing with a central force. So we can describe the problem as some psi e to the power I k z, and because of central force there is no phi dependence, f theta e to the power I k r. We can write it as I k r by r. That is the most general way to write spherical waves. And our main task is to find this f theta. Okay. So I described last time that I can expand this thing as a solution. So first let me write down the full solution of this in spherical basis. So K L M L R L K R. This is the spherical harmonics, so it should be written as the Y. And this thing is basically the spherical Bessel function in a generic free particle case. Free particle are constant potential. And as you know, in a central force problem, that is where all the potential and all the factor is. The theta phi part is always the same. So we rewrite these as psi k l m l, some normalization factor j l k r. You can rewrite it also in terms of this Legendre function. And when you expand this e to the power I k z in a general case, becomes C L J L K R times the PL, which is this Legendre function. Okay. And then I mentioned that how to calculate it. I didn't, of course, do it in the class, and it is worked out in my notes. So when you do that, this using the orthogonality property of this Legendre function, you get I to the power L 2L plus 1 JL KR PL cos theta. Okay. So we rewrite this in asymptotic case, asymptotic form, expressing this in asymptotes. Note that there are some typos at this place in my note, which I noticed later, and I will suggest you to fix it. I mean, that's part of your consider it as an assignment. I will write it correctly, try to write it correctly here, but it's written wrongly in my board, not here, after some equations. 2ik to the power minus ikr by r minus 1 to the power L. So this is your incoming wave form, and as I told earlier that the point of this partial wave method is that you will think every point of a spherical wave is like every point of the plane wave is like a spherical wave, and the scatterer basically scatters those spherical waves. So you want to write the full wave function also in this form. So full wave function at large R. Here is the typo. The typo is I dropped this 2L plus 1 somewhere. So this 2L plus 1 should be there. Let me write it here. Okay. So this full R should be minus 1 to the power L. So this part will be there plus the f theta, the factor, the outgoing factor. So these two together, actually I can rewrite it as some SL, which is my incoming outgoing wave S matrix, IKR by R. So this should be the full factor with a 2L plus 1. Check the small factors of half, minus, plus, all those things. But I think this is roughly the correct expression. This is this plus the outgoing wave, okay, which has this additional S factor. So this I argued also earlier that since conservation of probability must be there, so this must be a phase. So e to the power 2I delta L. And this must be, this thing is this plus f theta, the f theta factor, right? This is this plus the f theta factor. So the f theta must be basically 1 plus SL. So 1 minus SL minus 1. So it is sum over 2L plus 1. Yeah, everything is correct from here onwards. So couple of equations are wrong. Okay, so this must be the f theta. So now I can do a little bit of algebra and write it a little simpler way. So then this becomes sin delta L. I want to retain this e to the power form, so I rewrite it as, I multiply it by e to the power I delta L, and then I get this expression. So this is my f theta, and from here I can work out the differential cross section and full cross section very simply. The differential cross section will be d sigma d omega mod f theta square. So basically it's a sum. So two sums and then square. So it should be L prime 2L plus 1 PL C theta sin delta L e to the power I delta L is suffix by K times the same object PL prime 2L plus 1 times 2L prime plus 1 PL prime. I am not writing the cos theta sin delta L prime to the power I delta L prime by K. So this should be summed over this, and the integral, which using orthogonality of this can be written as, for a given L channel, I am separating the L part now, 4 pi by K square. You can write also the total cross section by writing the sum over L. Okay. So this is the full total elastic cross section for a central force at given L. The information about the central force is still not explicit. It's hidden inside the delta L, and I'll show how to calculate it. Okay. Now there is a theorem which is usually stated this thing as a optical theorem, which is basically nothing but the theta equal to, so this we learned that this is how you want to see the scattering. This angle is theta. So theta equal to 0, basically the forward scattering. This thing has a special name because it was first worked out for physical optics in using classical physical optics by Rayleigh. So this thing is called forward scattering cross section. This has some important. It's basically, you can say it's the fact that the straight goes without any scattering. So what's the probability of that? Forward scattering cross section. And this thing has a name which is for historical reason because it came from there. So PL C theta becomes 1 and imaginary F theta equal to 0 becomes in total cross section. So sigma L becomes 4 pi by K imaginary F theta equal to 0. So this thing has a name, it's called optical theorem. Okay. Okay, so this is basically the main idea of, or all the things we wanted to calculate, all the quantities we defined, the scattering power of a potential, and everything boils down to a very cute formula where the only unknown is this delta L. That's the only thing we have to learn how to find. Now there is one more thing which I have missed, that in the classical description I have talked about something called impact parameter, and that impact parameter seem to have no meaning in this quantum description, because now the picture is, it's a plane wave, it's a plane wave which is coming here and scattering like that. So then in classical we think it is like that. Now there is no trajectory in quantum mechanics. So how do we make sense of this impact parameter? Impact parameter is a physically important thing because you need to have a notion that if you throw the particle which is very far away from the event or the scattering center, there must be some phenomena that will describe that it was thrown too far away or it is exactly in the line of the scatterer. So we will invoke some semi-classical description to bring in the impact parameter in this description. Let me actually wipe this, it looks weird. semi-classical picture to make sense of the impact parameter. So we will use some dimensional analysis and give a semi-classical understanding for this. So notice that this impact parameter, you can link this with the angular momentum as writing it as BP is LH bar, because effectively this is like the distance and it's dimensionally same as angular momentum. So you will like to bring an impact parameter in the picture from the angular momentum, which makes sense here, from the angular momentum of the spherical wave or the spherical component of the plane wave that must have a impact parameter associated with it. Then you want to say that what does it mean physically? This is actually similar to the idea of Fresnel zones in optics. Did anybody of you studied Fresnel zones in optics? Online, local? Online audience? Are you there? Anybody there? Alive? Awake? What? Can you hear me? Are you there? You can write in chat. Okay, fine. Okay, that's enough. Okay, let's not expect anything. So now I want to describe this thing. These impact regions, this is B and this is, let's say, the next region. So this annular region, I want to describe it in terms of some B, that is LH bar by P. This is the inner one, and the outer one is L plus 1 H bar by. That's a minimum gap you can have in L. Right? That's the, you cannot have anything smaller than that. So in semi-classical sense, I am associating this with some kind of a physical distance. Okay?
What is the argument that it will, does that dimensions?
Yeah. I am trying to bring in a picture. So I will. There is a little more than that. Let me come to that. So right now I'm just matching dimension, and I'm trying to bring an impact parameter into picture. And this is not entirely like a dimensional matching, because if you plot this guy, these 2L plus 1, which is the factor that is contributing here, 2L plus 1 JL KR. This thing is basically like this for L equal to 0, and like this for L equal to 1, and similarly something like this for L equal to 2. So the main point is, given a L, the contribution is maximum peaked here or here or here, like L equal to 1 or L equal to 2. So you can associate this. So this is a spherical picture, right? So you can associate this with this kind of impact region. So what you are trying to say, this L plus L equal to 0 or L equal to 1 or L equal to 2, they are basically this maximally peaked at this distance. So that's why it makes sense to associate this momentum with this angular momentum with a physical distance B. Understood? Doesn't sound very happy. Doesn't look very happy. Yeah.
So the point of the impact parameter was to see how close it
Yes.
is to that
Yes.
line, right?
Yes.
And then what you're saying is that for integral values of L, at certain point it gets.
So if you see the plane wave is decomposed into spherical waves, right? So these spherical waves have maximal probability for 0 here, then it fades away, right? Then it fades away, then it is here. If I see this thing away from this plane, okay, as if the particle is coming like this, this is the L equal to 0, this is L equal to 1, this is L equal to 2, right? So I'm viewing this and momentum, angular momentum, as something equivalent to impact parameter. It is quantum probability, right? It's there in between, but the probability is peaked there. Okay, so this is the link between the classical notion of impact parameter and this quantum angular momentum. You cannot think it in the same sense as classical because there is no trajectory. So this is the best link you can make with impact parameter and this angular momentum. Right. So this is exactly same as the Fresnel zones in optics. If you have read that, you can look up in Hecht. But this idea is exactly same. Okay. So now I want to bring this into our analysis. That and another thing to notice that this is also related to the angular momentum. So let me write it K actually. Linear momentum. Okay. So now what I want to say that now the notion of impact parameter is in terms of this. So this is also associated with the momentum here because as the momentum is, if the momentum is large, then from a given angular momentum, the impact parameter will be small. Right? So we would like to bring this by saying, so then we say that if k is very small, and for then you are likely to expect that the B is also like the L equal to 0 is the maximal contributing factor. You can plot this also here and see that. So that means if you have a soft scattering means if you have a very low momentum particle, very low linear momentum particle, very low linear momentum, then the most probable contribution will come from L equal to 0. So you have a plane wave which is written in terms of these spherical waves. Okay. So the maximal probability will be for the L equal to 0 if the momentum is low. Okay. So this L equal to 0 mode is called S wave. And this is exactly the same you have done in hydrogen atom. This is the P wave. So S wave, P wave, and all this scattering contribution will come depending on the linear momentum. Okay. And you will also want to have the notion of missing the particle altogether. So if your B is somehow greater than A, so A is basically some physical bound of the object, where you are trying to get this impact. So you replace this B by some LH bar by K. Okay. So angular momentum must be equivalent statement is, and if the angular momentum is greater than AK, or in other words, if the momentum, linear momentum is too less, then it's likely to not see this scatterer. Okay. So this is basically this is the analogy of impact parameter in this fully quantum picture. Okay. And that is basically what I wanted to tell about all about the scattering. Modulo, I have not yet told you how to solve the delta L. So that is what I will do next. So all the physical picture and setup of the problem is clear so far?
Sir, here for the maximum contribution is the idea that whatever order K, like the classical momentum, that will have the maximum.
Yeah. This is KR. Yeah.
So what, like, with reference to LH bar, whatever the classical momentum order is.
Yes. So that contribution will be relatively much higher than all other contributions for smaller K.
Classical, right? Classical, we would expect that if we decrease the contribution.
Which contribution?
Classical, if we take the closer it is to that.
No, there is no classical analogy to that. What I am trying to say. So first of all, there is no. So you cannot think in terms of impact parameter, but you have to think in terms of the L parameter. So the way to think about this is, if your classical momentum, so B, if your classical momentum is too tiny, okay, So then classical, your linear projectile momentum is too tiny, then the most contributing factor will be small l. Right? So this is the equivalent analogy. So if you, in a quantum picture, it means if you throw a particle, the particle will, this will move like this, which is equivalently represented by this picture. And the statement is as k goes to 0, then the relative contribution of this center becomes higher compared to the lower.
Momentum it gets analogous to.
Yeah, low momentum is analogous to closer to origin. So this is the analogous picture.
But for higher momentum, we can't make any such statements, right?
Yes, the opposite statement is also true. So more is the linear momentum, more you have contribution from this higher modes. And the relative weight, this relative height is also less because this relative height is 2L proportional to L.
And this particular, the other side motion we don't have in classical, right?
No, the other side motion is of course. No, there you can also think what happens in this side, right? So notice this expression. This expression has no. This expression has all kind of components. So this expression is basically the full picture of this. So this expression is the full picture of this. So what I'm trying to say that the total scattering power of the object, where is the contribution coming from? So that contribution is mostly coming from for the low L mode if your momentum is low. Okay, so this is the full picture. So this what happens in, what happens out is all encoded in that because this is contains the delta L.
My only question is that for the for the low momentum case, it makes sense if we even in classical, right? But there is no classical analogy for the higher L.
No, there is. So the classical analogy is so. Oh, wait, okay. So first of all, you cannot think in terms of an impact parameter at all in this problem. Okay, but
we did the whole thing because we wanted some semi-classical.
yes. So the semi-classical notion is that because B is a fixed quantity, we are not playing with the B here. When we are trying to making this analogy, we are not playing with the B. We are playing entirely in terms of the momentum. Because in quantum sense, the distance really doesn't matter. Okay, so this is the momentum is what decides everything. Yes.
Should be L because K should be same as
What should be LH cross should be?
because H cross K is linear momentum and angular momentum, so there is a dimension.
Where? In this equation?
H cross K is T
Hmm.
as the dimension of linear momentum, but on that side it's not balanced properly.
No, LH cut is the angular momentum, right? What do you learn in board principle? It's the angular momentum is quantized as LH cut, right?
Oh, I thought L to be something. L is a
What did?
number.
Yes. What were you thinking?
I was thinking L as well.
LS?
L. Like I confused with length.
Okay. Are you not sleeping any nights? I mean, how can you went in that direction? Okay, I think you need some nap or. That's okay. Yeah, I don't have to explain. It happens. Okay. So now I will talk about how to calculate this delta L. Okay. So now your whole exercise is now to calculate the delta L, that is the partial FC. So how to calculate that? So there is a very simple prescription that I laid out in the notes. So let me write that. So first you solve this static Schrodinger equation. This whole thing boils down to a simple differential equation solving problem. H cut square by 2m that can. So you start with this solving this, and you want a trial solution which is of this form. So psi r P A C theta UL KR by R. So why I am writing it JL as this form, that will be clear in a moment, because in the asymptotic limit of free particle I want this to coincide with JL. So it's a choice to write it like that. And E is, note that we are solving the asymptotic form. So this, if I plug in here, the radial equation for UL will become so you have to basically solve this equation. It's a purely radial equation, and this particular choice is, as I said, we want this UL to be in the asymptotic limit IKR, and this SL is basically this e to the power 2I delta L. So once I solve this U, then I fit in this asymptotic form. This also has a transert solution, which is this, and I work out the delta L. Okay. So this is the strategy, and basically this equation, let me give it a name. So this equation is equation number 1, and this condition that this should be the asymptotic form, let me call it equation number 2, and for nothing to, we don't want anything to blow up, because this JL is actually JL which is well behaved. So this UL KR must go to 0 as KR goes to 0. So these three things we want to solve, okay, and these three conditions we want to satisfy. These two are like boundary, this is the boundary condition, this is like a trial form, and this is the equation we want to solve. So once we solve these three things, solve this equation with these two conditions, final job is to calculate the F theta as 2L plus 1 to the power I delta L, I delta L by K PL cos theta. Okay. So that is it. So let me show you how to do that for one case. So notice this is nothing but using a unsurged solution which you know from the structure of the problem at asymptotic limit. Right? So that is all you are doing. It's a physical picture which we have developed so far, and we want to plug into the as a trial solution with the appropriate boundary condition and just solve a differential equation. That is where the whole thing boils down. So let me solve it for one case. So this is the spherical well problem. Spherical finite well. So I have a region where the potential is minus V naught. Did I take minus? Yeah, minus V naught in some radius A. So the potential is basically some theta function A minus A. Because I want, when it reaches here, it must jump like this. So it is like this, except it's a little difficult to picturize, because if I rotate this, it becomes 2D, but I want to rotate this in this way also. So it's a 3D picture. So inside the sphere, it is V naught. So I hope you got the picture. It's not a 1D well or 2D well like the one you solved. It's a 3D region, 3D spherical region where there is a potential minus V naught. And I am throwing a particle like this somewhere here. And in quantum picture, it's basically a plane wave which is coming from far, which again you can think in terms of decomposed into the spherical well, and we'll see that which momentum modes will be important. So let's say this is also attractive because of the minus sign. So it's an attractive potential. So look at the prescription. The prescription is to solve this. Okay. So the prescription is solve this equation. Now it's becoming an algorithmic job. 2m by h cut square p naught theta, and you have solved this kind of problems like millions of times probably, that it's a differential equation with it's effectively a 1D particle in a box problem, particle in a finite well problem, except it's not exactly 1D, it's half line because it's a radial coordinate, so 0 to infinity, not minus infinity to plus infinity. So let's say I want to solve for L equal to 0. So S wave scattering. This is particularly easy. So when you solve that, so let me skip some steps because it's very trivial how to solve that. So okay, one more step. I want to solve it with this trial form, right? That's what I said earlier. Minus S L equal to 0 e to the power I k r, and this boundary condition. Okay, this is my 3 steps of prescription, that what do I need to solve in order to solve this full equation, and that is what I will just plug in. So the solution will be following. At r less than a region, which means inside the sphere, it should be d2u dr2 by plugging in this trial solution, minus q square u, where q is 2m by h cut square e plus v naught. Okay. So this is a very trivial equation, and the solution is harmonic form in sine qr, and r greater than a, the solution will be, there will be no v, and you will get a form ur some other normalization factor n prime where k is 2m by h cut square e. Okay. And actually, no, this is correct. Okay. Now we will use these continuity equations. Continuity, that du dr and u are continuous, because that's what we did earlier to work out this kind of coefficients at r equal to a, and that will give me an expression like this. And if I solve for it, I will get S L equal to 0 e to the power minus 2i ka plus tan inverse k tan qa by q. Okay, that means the delta is let me write exp is 2 delta L. So delta L is, there is some sign I messed up here. So check that out. I think it will be minus Ka plus tan inverse K tan UA by Q. Okay. So this will be your expression of delta A, where the information about the V naught is hidden inside the Q. Okay, that is the Q expression. It's a very straightforward. The problem boils down to solving 1D particle in a well kind of problem in half line using the continuity and everything. You can work out the phase factor. And let me write. No, let me not write here. So it turns out this problem is. Let's try to build some more intuition from the solutions. So let's look at infinite well instead of finite well. I hope everyone is following at least the strategy, that it boils down to and appreciating the fact that how easy this problem is after you set up the formalism. So if someone asks you, for example, to calculate S wave scattering cross section or scattering or phase shift, then you should do this way. If you do ask P wave, then you have to add the L equal to 1 term. So this problem I am not going to solve because it worked out very explicitly in Griffiths. So hard sphere. So this was earlier it was a soft sphere, which means here it was minus V naught. Now I am taking this to infinity. It's particle in an infinite well. So then, which means it's unpenetrable, whatever energy you give. So this hard sphere problem, this delta n becomes these. These are two kinds of Bessel function, some JLKA, and you can show that at k going to 0 limit, this delta L is minus Ka to the power 2L plus 1. So this is a nice result to visualize it, say something physically. Is said that the phase shift is smaller or large L. Okay. And one more thing to note is this minus sign, this minus sign. So this minus sign it becomes positive if you use a repulsive potential. So it tells you the phase shift is a positive phase or negative phase depending on the nature of the potential. So there are a couple of other questions which you can do in it's worked out in various books, or maybe left as an exercise. One is this Yukawa type of, not exactly Yukawa, it is just a exponentially mu r. So this is not exactly a hard boundary of V naught, but it's fading, right? There is a fading region outside, which is exponentially fading away. And you can try also the Coulomb potential using this partial wave, but that is a little tricky. Okay, then there is one more point, is to visualize this kind of problem, the scattering power of a potential as a length scale. So this is a practice commonly done in many communities, like example, atomic molecular physics. People describe this scattering potential or scattering power instead of a cross section or a phase shift. They describe it as a length scale, scattering length. So I'll tell you in a moment how to describe that, how to associate a length scale with this. So there is one more thing which I should mention. There is something called threshold behavior, and I couldn't figure out why they called it threshold, whose threshold it is, but sometimes these names come very peculiarly. Like this golden rule, like why golden? Why out of all this? It's like some peculiar name. So threshold probably has some historical reason with something. So the idea is that this delta L modulo the sign is k to the power 12 plus 1. So Lth partial wave shift is lower, this behavior lower for short range potential, for large, for Lth partial wave is for this momentum. So this thing is called threshold behavior, and this length scale connection. So this once you know this delta L, which is k to the power 12 plus 1, you can calculate the quantity of interest, because in the cross section the quantity of interest is sine square delta L by k square. So that you can rewrite it as 1 by k square yeah, I think I am using something, doing something wrong here. Let me check what I need to calculate. Yeah, that's correct. So once you put all the tan cot behavior, then you get this. Yeah. So then this thing becomes k cot delta as square delta. You can rewrite it as some one. You can expand this, and this becomes some half gamma k square plus dot dot dot. So this object k cot delta at k going to 0 limit is minus 1 by as. So you can show this object has a dimension of inverse length, and sometimes the cross section is described entirely in terms of this as at low momentum. So this is called a scattering length scale. These are just some names. When you read some paper or read some book, sometimes people say the whole scattering phenomena is described in terms of a length scale instead of a phase or anything. So this is just to familiarize yourself with that kind of notation. So that is roughly everything I wanted to say about partial wave. The rest is just solving different problems with different potentials, and just familiarizing yourself with some physical notion that what happens in low momentum, what happens in high momentum, that sort of thing. So now we will move on to talk a little bit about the Green's function method. I will be, of course, not be able to complete it, and we will complete it properly next time. So pause here. Questions at this point?
So just a generic question. All these high momentum, low momentum, like what are these scales of momentum that we're talking about? When we say, let's say we take experimentally, when we take, let's say, low momentum,
it depends compared to the depth of the potential, right? So whether you want to talk about electron volt or mega electron volt or giga electron volt, that depends on the depth of the potential, which means, so this is momentum has a generic unit, but by scale you mean order of magnitude, right? Is that what you mean? Yeah. So it depends on, for example, to see a scattering, that to see a break a bound state, for example, or see some non-trivial scattering in a potential. So it depends on what is the strength of that potential, how deep is that. For example, here this is a impenetrable potential, right? This is because it's infinite. But if it is a finite well, then how much momentum will deviate the potential, or the amount of phase shift, that is where all this information is encoded, because this delta L is dependent on this Q, and this Q is basically decided by the V naught. So that is the scale is decided with respect to the V naught of the problem, that when there will be a significant phase shift to observe. So that depends on the V naught of the problem, and that is why you have people set up all these experiments, right? If you are doing a old days, people used to do this nuclear physics experiment that was mega electron volt scale scattering experiments. That was like these pelotons in TIFR or VECC. They have that kind of equipment. But then people wanted to probe strong interaction, weak interaction. Then they need giga electron volt. Now they need LHC, tera electron volt. So it depends. The momentum you need to probe a particular system, it depends on the depth of the well. It's a very crude way of saying how strong the interaction is. And in condensed matter, you usually need milli electron volt to electron volt range. That's a very low wave and mostly S wave scattering. Atomic molecular also, it's mostly S wave scattering. Okay, let's talk a little bit about the Green's function. So recap a little bit Green's function before next class, then next class will be very smooth. I don't, in case you have forgotten the Green's function method. So as I said, there are some typos in my note, so read it cautiously and compare it with the book. I mean, it's mostly from Griffiths. You can just look at Griffith and this partial wave and everything I'm talking so far is Griffith level. So the Green's function, so notice the problem we want to solve, the Schrodinger equation in this scattering problem. It can be rewritten in this form, where k square is this 2me by h cut square, psi r, 2m by h cut square, p r, psi r. So this is the problem we want to solve, and we'll solve it using this Green's function method. So we know that Green's function you can use for any linear operator. Lu is f. It can be matrix, it can be a differential equation, any linear operator. If we want to solve this, so let me call it a position operator. So if you know the solution of this problem, and you know the solution of this problem, if such a solution exists, then what is the main job? What we have to do to solve it? You have to invert this. Now, inverse of an operation, not always a very easy thing. Like if this is very nice linear matrix form, you can just invert it. But the strategy to do this job is basically this inverse operator is nothing but this Green's function. So the Green's function acts as an inversion operator. So once you know this, what you do, the solution is of this form: Vx plus the inverse operation this is the whole essence of Green's function, and that's what you learned in math methods and electrodynamics, I guess. And electrodynamics you definitely had done. So we will use this to solve this equation. So you need this solution, the homogeneous solution, which is this V, by setting it 0, and you need the Green's function for this operator to invert that operator and act it on this source term, which source term is this fx. Okay, and the simple strategy is to work out the G and write down that phi r is the homogeneous part, now this equation you can see that there is a bit of catch because this psi is here and here on both sides, left hand side and right sides, and that makes natural way for this Dyson series which we have learned earlier. And the strategy is to solve this and eventually connect it with this form. This is your incident or homogeneous wave when there is no potential. I assume this particular form, and this solution should help you to identify the f theta as a spherical wave, where psi r will be a spherical form. So this is the Green's function strategy we will use to calculate this f theta. So that is what we will do in the next class. And then there is a way to generalize it in bracket notation for a matrix form. So that is what also we will do if there is time, but generally I thought that I will leave that and straight move to relativistic quantum mechanics. Okay, can you see the quiz? Huh? Yes? Okay, good. Today it is working properly. It's a very easy quiz, so don't. All these quizzes are easy now because earlier average performance was not good. So be careful, don't be sloppy, and get full marks. It's quantum mechanics 1 level question. You can stop the recording.